The proof is in the pudding, just ask Jashawn Holden. Hi, I'm Ray Myers. Welcome back to Craft versus Cruft. We are spending some time with the Lean Prover today, my favorite proof assistant, in honor of the new book, The Proof in the Code by Kevin Harnett, as well as some other stuff I'm working on. I'm building a proof agent, which is the combination of a coding agent and a proof assistant. I've decided we should call that a proof agent. And a hump that took me a tremendous amount of time to get over was even understanding what these things do. How does formal methods work? What is formal verification? A proof assistant proves mathematical theorems, which means sometimes it can prove things about software, but only if that software has been defined as a mathematical entity. What does any of that mean, right? So I think one of the things that this thing needs to be able to do is help a user understand what exactly it's doing. I'm not in the school of thought that thinks it should just do a bunch of verification behind the scenes and this just means you won't need to understand. There's some degree of exchanging of understanding that needs to happen, and that is what I'm experimenting with today. Let me show you what I mean. I saw a post on LinkedIn where this fellow, Alex Otian at University of Bucharest, that their group has put together for educational purposes a certified compiler for the IMP programming language. That may not mean much to you, but it meant something to me because when I was trying to learn provers, a book I found very helpful, even though I ultimately hit a wall, was called Concrete Semantics. That was my introduction to the IMP programming language, which is an example imperative language. If you can solve the problems of verification on it, then you can go on and, eventually they were able to formalize a compiler for C called CompCert, which I'm somewhat obsessed with, right? So I really want to understand how that stuff got done. I hope to provide you with one more piece of content to orient you on this journey of understanding what a verified compiler is, how it can work, and, hopefully improve your understanding of what we can do with programming in the process. So anyway, I pulled down this repo, which is their IMP compiler that they've done in Lean. You can see, if you haven't used proof assistants, they're called tactic provers. They run tactics on the goal state, and these execute and transform the code over here. This isn't in the repo. This is just what you interact with as you're making it, and eventually you understand what to do next, and you prove it. It's like this little video game. This is very strange stuff to try and get into and understand. So I kind of understand now what it means when they say they've implemented a compiler in Lean. They've defined the semantics of the language, which is like this formal reference interpreter, and then they've proven that the compiler matches that semantics, but it'd be very difficult for me to explain to you how it is that is proven this. So using an agent and some other tools like Remotion, which makes videos programmatically, well, I'm clearly comfortable just using a microphone. There's also some synthetic speech, and that's using a local model called Kokoro that I was running on my laptop. There was some agentically created content here, but I hope it's clear a lot of love has gone into how this is presented, and any flaws in it are probably more likely to be just my not yet understanding how to teach the material. Without further ado, let's get ready for some big step operational semantics and verified compilers.
To see how this tiny verified compiler works, first meet the two languages it connects. The source is IMP, a tiny imperative language, just the essentials, a skip that does nothing, assignment, sequencing, an if, and a while loop. Its meaning is given by a semantics. Running a program transforms memory, taking a starting state to a final one, and that state-to-state behavior is exactly what the compiler must preserve. So what exactly is that meaning? It's a relation between a start state, a command, and an end state, and a state, written sigma, is just the memory, a map from variables to values. The relation is built from inference rules, one per kind of statement. Here's the one for assignment, the case our example hits. On paper it looks like a fraction. Above the bar, the expression evaluates in sigma to a number n. Below it, running x gets a take sigma to that same state, now with x bound to n. In Lean, that relation is defined like a data type, and each rule is one of its constructors, premise in as a hypothesis, conclusion out. So for our program, 2 plus 3 is 5, and x ends up bound to 5. Now the compilation target, our stand-in for an assembly language. It's a simple stack machine in the spirit of bytecode. There are no variables in its expressions. It computes on a stack instead. Push a literal, add, subtract, or multiply by popping 2 values and pushing the result. Load and store move values between memory and the stack, and jumps handle control flow. A configuration is 4 things: the code, the stack, the memory, and a program counter marking the next instruction to run. Compiling means turning an IMP program into a list of these instructions that lands in the same final memory. At the heart of compiler correctness is a square. Along the top edge, a program has a meaning, given by the language's semantics, run it, and you get a result. Down the left edge, the compiler turns that program into code. Along the bottom edge, the machine runs that code to its own result. The square commutes when the 2 routes agree: read off the program's meaning, or compile and run the machine, and you land on the very same memory. Let's make it concrete. Here is the square for a concrete program. Our running example, x gets 2 plus 3, hold onto those numbers. The semantics transform the starting memory into one where x is 5. The compiler produces this stack machine code, and correctness is the promise that running it ends in that very same memory. Whatever the program, the 2 routes agree. Really, the proof is a tree of lemmas. At the top, one theorem, the whole program claim resting on a couple of supporting lemmas, and at the very bottom, one small lemma per kind of expression. Each induction fans out into cases, one per kind of statement, then one per kind of expression. We'll follow a single path down the tree: a program, its assignment, that expression, and one operator case. Every other branch, shown faded, works the same way. One idea powers the whole proof: induction. Take expressions. Everyone is a number, a variable, or an operation on 2 smaller expressions. The recipe is always the same. Prove the smallest shapes directly, then show that whenever the parts are correct, their combination is 2. That settles all of them at once. The same recipe works for programs by their statements. The top theorem. It takes any program C, the states sigma and sigma prime, and any starting stack, and crucially the hypothesis H, a proof that the source program actually runs sigma to sigma prime. That assumed behavior is what we get to lean on. Conceptually, the compiled code reproduces it. Formally, there exists a fuel budget, more on fuel in a moment, such that executing the code from the start configuration returns the configuration with the final memory, sigma prime, and the program counter at the end of the code. First, the notation. Sigma is a memory state mapping variables to values. Sigma prime is the state after running. A configuration, written mu, is 4 things: code, stack, memory, and program counter. The double arrow is the semantics. Command C takes sigma to sigma prime. And execute runs a configuration capped at fuel steps. Why a cap? Lean functions must terminate, but a compiled program could loop. So the theorem just asks that some fuel is enough, which is exactly what it means to halt. Here a reused lemma, execute lemma, does the heavy lifting. It states that whenever the machine can reach a final configuration, some fuel budget is enough for execute to return it, turning a reachability path into a real fueled run. Applying it splits our goal into 2 obligations. First, the machine can reach the end configuration, the one carrying the final memory. Second, that configuration really is the last one, with nothing left to run. The first obligation is precisely the lemma 1 level down. The second is immediate. The program counter sits at the code's length, so nothing's left to run. The top theorem is done, the rest of the work is reaching that state. Strip away the fuel. Same inputs and the same hypothesis H, that the program runs sigma to sigma prime. Conceptually, the machine can run the whole compiled program to completion. Formally, there is a reachability path from the start, program counter 0 with memory sigma, to the end, memory sigma prime with the counter at the code's length. One new symbol, reachable. Like the semantics, it isn't a primitive, it's an inductive relation defined in the project, built from 2 constructors, a single machine step and chaining steps end to end. So reachable from one configuration to another just means the machine can get there in some number of steps. The rest is still with us. A configuration is still code, stack, memory, and counter, and the double arrow is still the language's semantics. To begin proving this lemma, unfold the compiler. The code is the command's body followed by a single stop. A workhorse lemma will meet it next, runs the body, with nothing before it, the prefix is empty, and just the stop after it, the suffix, leaving us parked at the stop, memory already final. One more step executes that stop, which simply moves the program counter to the code's length. This layer is done, and it rested entirely on the lemma below. The workhorse lemma, it adds two inputs, pre and suff, any code before and after the command, and keeps the hypothesis H that the command runs sigma to sigma prime. Conceptually, a single command does the right thing wherever it sits inside a larger program. Formally, in three parts, take any code before it and after it, then the machine can reach from the state at the command start, the state just past it, and the memory goes from sigma to sigma prime. Now the code is wrapped. A prefix, then the command's compiled code, then a suffix, and the double plus joining them is just list append. Those are arbitrary instructions before and after, and compile offset compiles a command starting at a given program counter. Reachable and the configuration tuple are exactly as before. Same recipe as before, now on programs. We split by how the program ran, one case for each kind of statement, skip, assignment, sequencing, if, and while. In each case, we show the machine reaches the right state, assuming the smaller commands already do. Take the assignment case, X gets an expression. First, we run the expression's code, and that step is a call to the leaf lemma, a exp, compile correct aux. It leaves the expression's value on the stack. Then one store step writes that value into memory, giving the updated state. The case is closed, and notice we've arrived exactly at the leaf our descent has been leading to. Down at the leaf, the expression result. Conceptually, running an expression's compiled code leaves its value on top of the stack. Formally, there exists a fuel such that executing the code returns the stack with the expression's value pushed on top and the program counter past the expression's code. Two new bits for expressions. Eval gives an expression's value in a memory state, and the double colon pushes a value onto the stack. The configuration tuple and execute are still the same as for whole programs. One wrinkle, and it's the same generalization we used for commands. A sub-expressions code never sits alone. It's embedded in a larger program. So again, we allow arbitrary code before it and after it, and just require that the machine can reach the state where this expression's value has been pushed. We induct on the shape of the expression, exactly the structural induction from before. Lean splits the proof into one case per shape, numerals and variables at the leaves, the operators in between. A quick word on a tactic you'll see at every leaf, CerImp with the machine set. That set bundles the stack machine's step function together with its helpers, how an instruction reads the stack, updates memory, and bumps the program counter. So CerImp machine just unfolds the machine's one-step semantics and lets the goal compute. For a push, the literal lands on the stack and the counter advances by one. Wherever a single instruction has to run, this is the tactic that runs it. The leaves are easy. A numeral compiles to a single push. One machine step runs it, the literal lands on the stack, the counter advances by one. This base case needs no assumptions, it simply holds. Now the interesting case, a sum. Its code is the first operand's code, then the second operand's code, then add. And here are the induction hypotheses, I1 and I2, each saying its operand's code already does the right thing. This is where assuming the parts work pays off. Recall that reachable just means the machine can get from one state to another in some number of steps. We string together two such journeys. The first, I1, runs the first operand's code, leaving its value 2 on the stack. The second journey, I2, runs the second operand's code. Now both values sit on the stack, 3 above 2, and the counter is parked at the add instruction. One final step executes add. It pops both operands and pushes their sum, 5, exactly a val of 2 plus 3. The combined case holds, given that the parts did. Induction ties it together, and that's the bottom of the one path we traced, from the top theorem all the way down to this leaf. To be fair, the rabbit hole does go slightly deeper than that. We walked a simpler leaf, a sum, but the trickiest case is the while loop. Rather than step through it, here's the shape of its compiled code and why it's valid. First, the conditions code runs, leaving true or false on the stack. A conditional jump reads it. If true, enter the body. If false, jump past the loop to the exit. After the body, an unconditional jump goes back to the condition. That back edge is the loop. The jump targets are just offsets, fixed at compile time from the block lengths. So the machine's control flow mirrors the semantics. The two branches are the while true and while false rules, and because the source loop terminates, our hypothesis, the machine halts too, so some fuel always suffices. Here is what proving that one case actually takes. It's the true branch of the while rule, in full, dozens of lines, mostly stepping the machine one instruction at a time, feeding the induction hypotheses back in, and grinding through program counter arithmetic. And you can spot the machine simp set doing the per instruction work. We won't step through it today. So that's the shape of it. One theorem, two layers of lemmas, a single induction principle. This compiler and its semantics preservation proof follow Concrete Semantics, Chapter 8, and the Stack Machine compiler from Software Foundations. The full Lean development is in the repository. Thanks for watching.
All right, well, thank you for taking part in this experiment. Leave a comment, what worked, what didn't, what should be explained in the next version of this, or is there a proof or result, informal verification you're interested in exploring this way? And as it's written in the Tao Te Ching, with patience, the most tangled cord may be undone.